Hi, we're Group 1. My name is Jordan. Following me will be Alex, Kennedy, and David. We're going to start on Chapter 6.1, which is the Reynolds number regimes. This is also the behavior at specific Reynolds numbers. We're starting with laminar flow, which are small natural disturbances. These happen with a Reynolds number that's below 2300. Next, we have our transitional period, which are intermittent bursts of turbulence. Lastly, we have our turbulent flow, which is continuous turbulence that has a Reynolds number above 4000. Moving on to 6.2 for our internal viscous flows. The entrance length is the flow that is developing and changing with respect to the x distance from the entrance. Our LE, which is the longest development length. After that relationship, pressure and distance become linear. Our laminar flow is given on our equation sheet as 0.06 times our Reynolds number, and our maximum value for our entrance length is 138 times the diameter, either found or given. In turbulent flow, the boundary layers grow faster and our LE is relatively shorter. Thank you.
Moving on to 6.3, which talks about head loss and the friction factor. Head loss in relation to wall shear stress can be calculated using this equation right here. And this equation is derived from the energy and momentum equations that we've used in past chapters. And it concludes that the head loss is proportional to shear stress at a wall. And for laminar flow, the general head loss equation is shown right here, where F is the Darcy friction factor. It's a function of the Reynolds number, relative roughness, and the duct shape. And an alternative form for this friction factor is this equation right here. For 6.4, it talks about fully developed laminar pipe flow, and laminar flow or Poisson flow occurs when the Reynolds number is less than 2300. And for a laminar pipe flow situation, the head loss would be calculated using this equation shown at the top here. And with wall shear, the Poisson flow friction factor becomes 64 divided by the Reynolds number.
Moving on to 6.5, turbulence modeling, we have two assumptions that density is constant, viscosity is constant, and there's no thermal interaction. Therefore, we only have equations for continuity and momentum, where we're generally solving for velocity and pressure with no slip at the wall, and we know the inlet and the outlet conditions. For momentum equation, we have equation C, which is the correlation or the fluctuating velocity equation. Finally, we have equation D, the logarithmic overlap layer. This takes the wall law and the defect law and finds overlap layer velocities.
All right, so moving on to turbulent pipe flow. In turbulent pipe flow, we have a friction factor that's causing the turbulence in the pipe. And so we would use the Moody chart to solve or to find that friction factor. We have relative roughness, which is epsilon over the diameter of the pipe, and then the Reynolds number right here, and then the friction factor that we're looking for. And so if you had the relative roughness available to you, you would follow the curve. And then if you also had your Reynolds number available to you, draw a vertical line wherever it crosses the curve, then a horizontal line over to find the friction factor. We also have these formulas that you can find the friction factor, the interpolation formula and the Holland explicit formula, which if you have these values available to you are also useful to finding the friction factor. And we also have 4 types of pipe flow problems. The first one is head loss. All you have to do is plug in the values that you're given into the head loss formula and you've solved it. The other 3 are less easygoing. You have to use interpolation, which just means you have to keep guessing and trying and then making sure that your guess goes along with what you actually solve for. If it doesn't, then you have to do it all over again with another guess. And then we have a schedule number, which is just the thickness of the pipe. And you would find that by dividing the maximum pressure by the allowable stress. And that's all. Thank you. Have a nice week. Hello, my name is Alex. I'm going to be presenting the problem for this week on behalf of my group. So I already have drawn out the scenario that's given to us in the problem, the 2 reservoirs connected by the annulus. And I've selected this portion to be my point 1 and this portion to be my point 2 for my Bernoulli equation. And so let me just go ahead and cross things out. I know that these 2 will cross out because both pressures are atmosphere and everything else would be the same because water and gravity is the same. And then these will cross out as well because velocity at the surface is 0, meaning that our head loss is just C1 minus C2, the difference between the 2 points, and that's given by 20 feet. So head loss is 20 feet. And so now I'm going to assume laminar flow and use the equation for laminar flow, the head loss equation for laminar flow, excuse me, which is 128 mu length of the annulus Q by rho G D4. So we're asked to find Q for the problem. And so I'm going to go ahead and do that. First, I need the diameter. And so the diameter of the annulus would be given by 4 times the area over the circumference. This was given in the problem. Area is pi r outer squared minus r inner squared. The circumference is 2 pi r outer plus r inner. So when I plug in the values for the radii, which are given right here, the inner is 0.5 inches, the outer is 1 inch. I get the diameter is 1 inch, which is about 0.08333 feet. And so now I have everything that I need to solve for Q. So I'm going to go ahead and write that equation. Q equals rho GD fourth power 128 mu L. So these are the values that I have for all of the ones that I need to solve for Q, mu rho G that haven't been mentioned yet, and L, that's the length of the annulus. So then I get Q equals 1.765 feet per second. And so then I can't stop here, even though the question just asked for the flow rate. I have to check to make sure that it's laminar flow. And so I have to find the velocity, which is easy, simple enough. We already know these values. Plug them in, get 107.8778 feet per second. And so we plug that into our Reynolds equation, rho v d over mu. Again, all values that we know. And we find that our Reynolds number is going to be 833.137, which is super big, way too big to be considered laminar flow. Therefore, we have to consider, or we know that it's turbulent flow. So we use this new head loss equation for turbulent flow, which means there's friction, d v squared over 2g. And so we're going to try and find v this time so that we can calculate the q based on the v. To find that, we're going to also need f. F is dependent on the relative roughness. This is a value that is given by the fact that we have commercial steel. And so the ratio ends up being 0.0018. Now we're going to go over to the Moody chart to find or estimate our first guess for the friction factor. So we're going to be looking here. So I have already written out a line for 0.0018, which is the relative roughness that we just calculated for our first estimate. We follow that all the way over here, and we find that it touches at around 0.225. And so that's going to be our first guess for the friction factor is 0.225. So then we would plug that in to find the velocity, rearranging the equation right here. So V is HF, DG, LF. So we know all those values, and we can plug them in to get 10.918 feet per second. And then the Reynolds number, we already know that equation, so I'm just going to give the answer for So I'm just going to say that's about 4.6 times 10 to the 5th. So now we go to the axis for Reynolds number. We're looking at the portion that's the 10 to the 5th. And so this is where I plotted my 4.6 times 10 to the 5th. Because if you look closely, this is about 4.5 is where that little pink dot is. This is what I'm estimating to be about 4.6. And so we're now going to look and recognize that there's a trend here. All the lines curve. And so even though our line was originally straight for our first guess, we're going to try and estimate the curve. And we see that there is a discrepancy between our curve, where our Reynolds number crosses our actual curve and where we estimated it would. So we're going to go ahead and get a second guess. I'm going to say that this is about 0.24. So F is, sorry, 0.24. 24. Using the same velocity equation, we're going to find that this time velocity is 10.572 feet per second. And then the Reynolds number would be 816.7.31. So as you can see, so this would be 8.2 times 10 to the 4th. So there's a pretty big discrepancy here, which means that we should probably do another guess, because even though we're saying that it crosses here, that's only considering the Reynolds number here. That's how we know that this, at this friction force, it crosses the curve. Oh, sorry, right here. And so we're gonna go ahead and make another guess. And let's see, based on this Reynolds number, we're gonna plot this Reynolds number now. And we're gonna say it's right about here. Here, it's a little bit smaller, so from 8 and then to 9, it's pretty small. So I just drew the line pretty close to the line of 8 because it's it's 8.2. And I found that based on my estimate of how the curve will go, it'll go right here. And we're just going to draw a line or follow the line that I already drew. And it goes right here. So I'm saying that that's about 0.0246. Again, it's a pretty crude estimate, but it's the best we can do. So we're going to make another guess, 0.0246 this time, because it's not quite 0.25. And the velocity at this guess is 10.44 feet per second. And then the Reynolds number is 80643.32119. And so that's about 8.1 times 10 to the 4th. And that's super close. Like if I were to draw a line for this Reynolds number, it would basically be the same one. And so that means that we're going to go with the friction factor that we found based on the two Reynolds numbers because they're so close. So we're going to say that that friction factor is 0.0246. That's our best guess. And or we can say that it converges is the proper term. And then so we can find, or we can use the velocity that we just found and then solve for Q using velocity 10.44 feet per second and the area that we have calculated already above. And we find that Q is 0.171 feet cubed per second. And that's it. Thank you. Have a nice day.